So now we're going to get started on the examples in this section. I think if the last video was a little bit too fast for you or too confusing, then I think these hands-on examples will help a lot. So here we want a confidence interval of 95.44%. That means that in terms of our distribution here, we want 95.44% of the area to live on the inside here. And remember, I'm calling that inside area 1 minus alpha, so that the area on the outside is called alpha. And that means that half of that alpha lives over here, and the other half of that alpha area lives over here. So in this case, 1 minus alpha, that's the area on the inside, that would be 0.9544. That means that alpha is going to be 1 minus 0.9544. So the area on the outside would be 0.0456. So that gives me alpha. So in this case, what we know is that the area on the outside of these vertical bars is 0.0456. So now what we can do with that information is we can start trying to find the z-score that has this particular boundary or this particular boundary covered. So we can find the z-score that has this alpha over 2 area to the right and the z-score that finds this alpha over 2 area to the left. In this entire section, though, we're mainly just going to be focused on the positive z-score. So that will be the z value that has alpha over 2 as its right area. And that's what this little section says. So z alpha is going to denote the z-score that has the area alpha to its right. So let's compute this first one. This is saying that we want the z-score that has an area of 0.05 to its right. So that's an area of 5% to its right. So if we want an area of 5% to the right, that would mean that we want an area of 0.95 to the left. And to find that area, what we can do is we can use the distribution tables that we used last week. So in this case, I want an area of 0.05 to the right, and therefore an area of 0.95 to the left. Now this is a table of left areas, so I'm looking at this section because I want an area of around 0.95 to the left. And what I see is that if I want an area of 0.95 to the left, my z-score should be something like 1.64 or 1.65. Okay. So I'm just going to round those. I'm going to say, actually, let's just average them. So I'll say that 1.645 is the z-score that we're looking for. Okay. So the z-score that we're looking for here is a 1.645. What that means is that this z-score over here would be 1.645. That has the appropriate area over here to the right. Now, if we wanted z sub alpha over 2, in this particular example, what we had is that this was our alpha up here. So that means that alpha over 2 is going to be 0.0456 divided by 2. And let me punch that into a calculator real quick. So I've got 0.0456 divided by 2. That ends up being something like 0.0228. So that's the area that we want to the right. So this is z sub 0.0228. Now, if this is the right area, then that means that the left area that we're looking for is 1 minus 0.0228, which is 0.9772. So just for more practice using the table, let's go ahead and find that area in the table. So we want a left area of 0.9772. So I will pull up the table. Whoops. Oh no. Sorry about this. Still getting a little bit used to the setup here. Okay, so we wanted 0.9772. So I'm looking for that in the table, and we can find it. It's down here. and that would correspond to a z-score of 2.00. So I can go back to the previous page, and what we just found is that, oh man, the z-score that we would look for here is 2.00. So these are the relevant z-scores. And now let's see how we can actually apply this in an example. So we're going to put this together with the formulas that we talked about a second ago. This formula in particular, which says that if you want the confidence interval for estimating a particular population mean, you can compute it using this information. And what we just saw is how to compute this z sub alpha over 2 part. We're now going to put together the entire thing in order to compute a confidence interval. Okay, so let's look at example 2. In example 2, it says the age of 50 people in the civilian labor workforce are randomly selected. Find the 95% confidence interval for the mean age of all people in the civilian labor force if the sample mean age is 36.4 years. So in other words, you've sampled 50 people and you found the sample mean of 36.4, and now what we want to do is estimate some sort of a confidence interval for the actual mean age of all of the people. So we're trying to, again, sort of estimate the population mean, but this time we're going to do it with a confidence interval. So here we're going to go through all of the steps that are required. Notice that in these problems, we are told the population standard deviation. That's important. So in these first few examples, we're going to just be told that the population standard deviation is 12.1. And notice that in this case, because we are sampling 50 people, that is a large enough number for us to expect that the X-bar distribution is normally distributed. So that means that we can use these drawings that I've been drawing so far. X-bar should be normally distributed. So in step 1, we're just going to do what we did a second ago. We want a 95% confidence interval. So that means that alpha is equal to 0.05, that's the area on the outside, and therefore z sub alpha over 2 would be the z-score that has a 0.025 area to the right of it, and that's something that we've already looked up, I believe. Let me just double check that. Oh, we haven't checked that one. Okay, so let's go ahead and look this one up then, just to get a little bit more practice. I do want to remind you that there are a lot of these listed up here in this table, so we could just find the appropriate z sub alpha over 2 from this table, but I think just to get a little bit more practice using the big table, let's go ahead and look up the appropriate area in that table. But you're welcome to use this little abbreviated table in this section of the notes if you'd like. So if you want a right area, oh no. So here you want a right area of 0.025, and that means that we want a left area of a 0.975. No, that's not right. Sorry. We want a right area of, oh no, that is right. Sorry, I shifted a decimal place for some reason. Okay, so we have a left area of 0.975. That's the area that we want to look up in the table, because remember the table is a table of left areas. So I'll look that up in the table, 0.975. Sorry, I'm really struggling. Okay, so we're looking for a 0.975, and you can actually find it exactly in the table. It lives here. So we're looking for the corresponding z value to that area. The corresponding z value, it looks like, would be a 1.96. So if you ever need to pause the video and check your own table, then you're welcome to do that. I just wanted us to get a little more familiar with looking up z values in this table. But if you want a left area of 0.975, then the corresponding z-value would be 1.96. So that's what we find here. And that means that the z-value that goes here is a 1.96. That's also the z-value that you would get if you had just used the small table that lives in this section of notes. So you don't always have to use the big table, but just to get a little more practice with it, I thought we might. Okay, so that's the z-value that we found. And now in step 2, what we're going to do is determine the confidence interval. And the confidence interval is the one that's given in this section of notes up here at the top. This starred formula is the one that tells you the confidence interval. It'll be that mu bar lives between this left endpoint and this right endpoint. So that will be the confidence interval that we write down, but now we know all of the individual pieces that we need for the confidence interval. So we know that x bar, the sample mean, is 36.4. We know that z sub alpha over 2 in this case is 1.96. And we know sigma and n. Remember, sigma here is the population standard deviation, and n was our sample size. So if I put all of that together, what we can say is that we can be 95% sure, because we chose a 95% confidence interval, that mu lives between x bar minus z, so between this endpoint and this endpoint. So we can be 95% sure that mu lives between 36.4 minus that z-score times sigma over the square root of n, and 36.4 plus that z-score times sigma over the square root of n. So I'm just plugging in all of that information, but this is something that you could plug into a calculator, and this is something that you can plug into a calculator. And if you do that, what you'll get is that mu lives between 33.0 and 39.8 with a 95% probability. So notice that here the estimate that we're getting is not just a single point, this is an interval estimate. What it says is that we can be 95% sure that mu lives between 33 and 39.8. And that's step 3, just to interpret that. So we are 95% sure that mu is between 33.0 and 39.8. Okay. So that's all that we're looking for here. Now, in example 3, so this is the last example that we'll do in this video. This is also the last example from section 7.1. So in example 3, we're doing something similar, only in this case, what we're trying to do is determine the sample size that you would need in order to achieve a specific confidence within a specific error. So in this case, we want to know how many people would you need to survey in order to be 95% sure that mu, the actual population mean, is within plus or minus 0.5 from your x bar. And here we're using the same data set, so we're still assuming that the actual population standard deviation is 12.1. So for this, what we're going to use is the second formula that I talked about at the beginning here. That's this one. It says finding the necessary sample size needed to estimate mu. Now remember, this formula that we got up at the top right here is just a rearrangement of the formula that we derived at the very beginning of this video series in terms of the error. So this e in the denominator here is going to represent the error that we're willing to put up with. So I'll go ahead and copy down this formula again down here. So the formula that we're going to use is that n is equal to z sub alpha over 2 times sigma divided by the error squared. So that's just me copying down the formula from up above. And now notice that in order to compute the sample size that we need to know the confidence level that we need. That's what tells us alpha. And we also need to know a certain amount of error that we're willing to put up with. So in this particular case, we'll figure out z sub alpha over 2 in a second, but we know sigma already is 12.1, and we know that the error that we're willing to put up with is a 0.5. So that underlined portion up here is describing the amount of error that we're okay with. And now I need to find z sub alpha over 2. That's, remember, the z-score that you would need if you want 95% confidence here in the middle. And if you want 95% confidence in the middle, that means that this alpha over 2 here is going to be a 2.5% on the left side and 2.5% on the right side. Okay, but I'll go ahead and tell you the shortcut that I expect you to be using here. If you have a 95% confidence need, then you can do the procedure that we used in these previous examples for determining the z-score, the same thing that we did in Chapter 6, but you can also just start using this table up here at the top of the page. In this table, you can just look up the degree of confidence that you need, and it will tell you the corresponding alpha, the area on the outside, or the z sub alpha over 2 measurement that you need in these formulas. So notice that here, if you want a 95% confidence, then that corresponds to a z sub alpha over 2 of 1.96, like we saw in that previous example. So if you want to just use this table as a little bit of a shortcut, you can. The z sub alpha over 2 that we need in this particular case is 1.96. So I'll just scroll back down and apply that. So this would be, this would be a 1.96 as the z times 12.1 all over 0.5 squared. And now maybe let me plug that into a calculator real quick. So if we plug that into our calculator, what we'll get is a 1.96 times a 12.1 divided by 0.5, and then all of that should be squared. And if we do that, we get a 2249.79. Now remember, this is supposed to represent the sample size. So what I'd like for you to do in cases like this is just round it up. So in other words, I'm not going to survey some decimal number of people. Instead, what I should say is that we should survey 2250 people. So the N that we would need in order to be that confident is 2250. So if you sample 2,250 people, then we can be 95% sure that our sample mean is within 0.5 of the actual mean. Okay. And now in part B, it says, let's find the 95% confidence interval if your sample has a mean age. So if your sample of the size determined above has a mean age of 38.8 years. So here what this says is that x bar is equal to 38.8. Okay. And now remember that the confidence interval is this. It says that x bar lives within, or sorry, mu lives within x bar plus or minus z sub alpha over 2 times sigma over the square root of n. So this is what's going to give us our interval. And now we know the x bar value. So x bar is 38.8. And then this will be plus or minus z sub alpha over 2. We computed that above to be 1.96. Oops, 1.96. And then times sigma, which is 12.1 over the square root of n. In this case, n was 2250. That's what we computed in part A. So we want 38.8 plus or minus 1.96 times 12.1 divided by the square root of 2250. And if we punch that into a calculator, maybe let me do that as well. Then what we end up getting is if you do the subtraction, then the left endpoint, or sorry, let's do the addition first. So if you do the addition first, then what you'll get is the right endpoint is 39.3. And if you do the subtraction instead, so if you put a minus sign between those two terms, then you'll get a 38.3. And what we know is that there's a 95% chance that the actual population mean will live between those two numbers. Okay, so this is sort of the general procedure that we're going to use in order to determine these confidence intervals. Now, the procedure that we're taking here requires us to know sigma. In the next section, we'll talk about how to approach these problems if you don't know sigma. In other words, if you don't know what the population standard deviation is. Okay, so that'll conclude section 7.1. We'll start with section 7.2 in our next video. But remember that if you need to read some additional examples, then what I'd recommend is you can either use the free textbook that I posted in the additional resources portion of the Blackboard page, or if you can, just locate a PDF of the actual course textbook, and you should be able to read some extra examples there. So hopefully that helps. Feel free to email me if you have any questions, and we'll get started on the next video soon.